All right, today we're playing the role of a mathematical detective. We've got a cold case on our hands, and our main suspect is a ninth-degree polynomial that, let's be honest, looks completely unsolvable. But just like any good detective story, there's a hidden clue that's about to change everything. So take a look at this. Seriously, if this equation landed on your desk, where would you even start? It's an absolute beast. You might think brute force calculation is the only way, but any good detective knows there's always a smarter path.
And here it is, in all its glory. Meet our antagonist, a massive, intimidating ninth-degree polynomial. You've got 9 different powers of x, and these gigantic coefficients. Our job? Find the value of x that makes this entire thing equal to 0.
Okay, let's officially open the case file on what we're calling this mathematical monster. Our goal isn't to fight it head-on, because that would be a nightmare. Our goal is to outsmart it.
And this right here is our whole strategy. We are not going to try and solve this thing with brute force. No way. Instead, we're going to be detectives. We're going to look for hidden patterns buried inside all those huge numbers. The coefficients themselves, those are the clues we need to follow.
So, with that in mind, let's start the actual investigation. And like any good detective, we need the right tools for the job, and we need a clear procedure to follow. It's time to gather some evidence before we make any moves. Okay, so here's our evidence bag. These are the 9 key coefficients from that monster polynomial. The source material calls them L sub q values. Every single one of these numbers from that first -45 all the way down to the bottom is a critical clue that we're going to use in our investigation.
And this is our method of investigation. It's a really simple 4-step process. First, we're going to pick a test number k, starting with 0. Then, we plug our coefficients into a special formula that's designed to test the underlying structure of the polynomial. Think of it like a forensic test, something that reveals a hidden property. We'll calculate the result, and then we'll just repeat the process. This methodical approach, it's about to reveal everything.
Okay, this brings us to the heart of the investigation. We're about to run our tests, and I promise you, the results are going to expose a pattern so shocking, it's the one clue that's going to crack this case wide open.
All right, first test is up. We're using our test number k equals 0. We run it through the process with our whole list of coefficients, and the result we get back is
0. Okay, that's interesting. But one data point isn't really a pattern, so let's keep going.
All right, next up, our second test, where k equals 1. We're going to follow the exact same procedure, run the numbers, and we get 0. Again. Okay, wait a minute. Now we're talking. That is a clue. Getting 0 twice in a row, that's not a coincidence. I think we just stumbled onto something big here.
And this right here is the breakthrough moment. We keep the process going. For k equals 2, you guessed it, 0. For k equals 3, 0 again. It doesn't matter what test number we use, the result is always the same. This is an unmistakable, undeniable pattern.
I mean, just let that sink in for a second. This isn't just some weird fluke. This is a fundamental property of this entire equation. Every single one of our tests, from k equals 0 all the way to k equals 9, came back as a perfect 0. This is the smoking gun we have been searching for.
So we've got our smoking gun. With this critical piece of evidence in hand, we are ready to close this case. It's time to reveal what this incredible 0 pattern actually means, and finally solve this thing once and for all.
You see, that consistent 0 result tells us something really deep about the way this polynomial is built. It means that all that crazy complexity, all those huge, scary numbers, it's all just a big illusion. They aren't random at all. They're perfectly balanced to cancel each other out.
And here it is, the big reveal, the aha moment. Our investigation proved that all the complex terms in this monster equation are hiding a very simple truth. That 0 pattern is evidence that all 9 of the equation's solutions or roots are identical. And when all the roots are the same, the problem collapses from that monster on the left into the incredibly simple idea on the right.
So because we know all the roots are identical, we can use a really cool shortcut. There's a rule in algebra that connects the coefficients of a polynomial right back to the sum of its roots. And in our case, that rule points us directly to our very first clue, that L sub 0 coefficient, which was -45.
And believe it or not, this is the final calculation. That rule says the sum of all 9 of our identical roots is simply that first coefficient, -45. So to find the value of just one of those roots, well, we just divide -45 by 9. I mean, After that whole journey, it's almost funny how simple it is.
And there you have it, -5. That's the solution to this entire mystery. That huge monstrous equation was hiding a simple integer all along. Case closed.
So, what's the big takeaway here? I think there are a few. First, even the most terrifying-looking problems can be hiding a really simple, elegant secret. Second, a methodical, patient process, that's your best friend for finding those hidden patterns. And finally, cracking the case isn't always about being a human calculator. It's about being a detective and finding the right key to unlock it. It really makes you wonder, doesn't it? What other amazing secrets are hiding inside the next complex equation? Just waiting for the right detective to come along and find them. The hunt is always on. Thanks for joining me on this one.